Hello, everybody. My name is Dimitri Kiritsis. I am the chair of the Department of Mechanical Engineering in Khalifa University. And on behalf of the UAE section of the American Society of Mechanical Engineers, as well as the Research and Innovation Center on CO2 and Hydrogen at Khalifa University, I would like to welcome you today to a talk by Professor Jaal Ghandhi with the title, "Are Batteries Going to Substitute Internal Combustion Engines?" Before we proceed, two pieces of logistics. First of all, I will ask that all attendees kindly mute themselves so that we avoid interference. Very soon, Professor Gandhi's talk will commence, and if you have questions, please put them in the discussion, the chat section of this session. We will have reasonable time for questions at the end of the talk, and I will try to pick some representatives once and share them with Professor Gandhi. And of course, if your question is picked, feel free to join. I will only talk a little bit about the two entities co-organizing this event. The UAE section of the American Society of Mechanical Engineers is the most recent national section of the society. It was the first national section to be inaugurated after 15 years, and the effort that we see today is mainly realized through the leadership of Dr. Bashar Al-Hassauni and his leadership team. And we are really grateful to the people in SME that provided the support that made this talk possible. The other entity is the Research and Innovation Center on Carbon Dioxide and Hydrogen, which is directed by Professor Lourdes Vega of our Department of Chemical Engineering, who is in the audience, I see. And it is a thematically focused center on sustainability and carbon neutral energy, as well as, of course, the exploration of hydrogen economy. So it is only appropriate given the combination of these entities, that today we will hear from Professor Jaal Ghandhi, who is the Granger Professor of Sustainable Energy in the Department of Mechanical Engineering at the University of Wisconsin-Madison. Jaal has indicated that he has an introduction about himself, so that I will not go long into his impressive achievements, professional achievements. I will only say that he is a fellow of our society, fellow of the ASME, as well as of the Society of Automotive Engineers. And you will allow me a small personal note before yielding the floor. Jaal has personified for me as a senior graduate student in Princeton, in the lab where I and he did our PhDs, the affection and wisdom with which what then was his nation surrounded and embraced an immigrant with two pieces of bags from the Eastern Mediterranean, and not only allowed him to fulfill his full professional potential and perhaps more than what he deserved, but also ultimately made him proud in calling what was then Jaal's nation also my nation. Without further ado, please welcome Professor Jaal Ghandhi. Jaal.
Well, thank you very much, Dimitri. So let me go ahead and share. Hopefully you are seeing my screen now. And we're good to go. So Dimitri, can you confirm that you see my screen?
Unfortunately, no.
Oh, okay. What do you see?
I see like small, small boxes with the names of all of us. Mr. Karam, can you help?
Oh, hold on, I think, is that better?
That's much better.
Yeah,
Okay.
that is now working, please.
Okay, one more button I had to hit. Got it. So, okay, well, let's go ahead and get started then. Okay, so today's agenda, I'm going to give you a brief introduction about myself, and the purpose for that is not for self-promotion, but the topic we're going to talk about is an important one to make sure everyone understands the bias of the person doing the talking. So I will tell you about my background so that you know my bias as you hear me talk about the problem. The next thing is that, you know, one of the things I learned at Princeton is that never offer an answer until you know the problem that you're trying to solve. And so we're going to try to define the problem in a way that we can formulate a solution. We'll go through some discussion of comparison of liquid fuels and batteries, and that will sort of really blend together with the comparison for different application sectors, okay? And for today, I'm going to talk about light duty, heavy duty, on-road, and then really just a very brief comment or two about heavy duty off-road vehicles. So about myself, right? So I got my bachelor's and master's in mechanical engineering at the University of Wisconsin-Madison. Went on to Princeton, where I received my PhD, and then joined the faculty here at the University of Wisconsin at Madison. Currently, as Professor Carissa said, I am the Granger Professor of Sustainable Energy. The two main professional societies that I am part of would be ASME and SAE, and I'm a fellow in both of those. And during my time at the University of Wisconsin in particular, I have been part of the Engine Research Center. So I did my master's degree in the Engine Research Center, and I am a faculty member as part of the Engine Research Center as well. And over the years, I've done a variety of different types of work. A lot of it has been optical in nature. So this is just sort of a demonstration. The top, what you're seeing, this movie, are in-cylinder visualizations of different types of engine combustion. So homogeneous charge, compression ignition, spark ignition, and diesel. The key feature here, these are obviously taken at different times, is the speed of combustion, right? And the speed of combustion is really related to the efficiency. And so the time scale for each of those three movies was the same, and you see how fast the HCCI was, and how slow the spark ignition combustion was. The bottom picture here is a simultaneous visualization of fuel. So the sort of bluish color represents the fuel concentration. That's being measured with a planar laser sheet. The red color is the hydroxyl radical fluorescence that's being produced from this laser sheet. By choosing the wavelength right, you can simultaneously excite both the fuel and the hydroxyl radical. Obviously, the hydroxyl is in the burnt gas, the fuel is unburnt. The top row represents a homogeneous condition, and you see there's no fuel in this black region here. Obviously, that area is full of OH, so that's the burnt region. When we put the two together, when I overlay them in the center column here, you see it's sort of like a jigsaw puzzle. The bottom row is a direct injection case where the fuel is not homogeneous. So you see stratification in the fuel, and you see regions, let's say here where the pointer is, where there's very low fuel concentration, but there's no OH, and that tells us that that just means that it's not burnt, and that's not why the fuel is gone, but it's just inhomogeneous. There's a picture here about planar measurements of velocity fields. This is actually part of a movie that we've done a lot of work with velocity and turbulence, fundamental turbulence measurements in engines as well. So I'm, if you will, a dyed-in-the-wool engine combustion person. Okay, so that's my background and relevant to the problem that we're about to discuss. Okay, so let's then define the problem, right? So if we're going to try to compare batteries and engines, we need to know on what grounds we're going to do the comparison. Okay, so first possible choice is local air quality, right? So all of us, I think, enjoy breathing clean air. And there's obviously a difference, if you will, between batteries and engines in that regard. But my argument for this is that the legislative environment is going to control this problem. Okay, so engines have been regulated for 50 years now in terms of pollutant emissions. That has done made major advances in terms of air quality, and as needed, I would argue that that's going to continue to happen locally, and it's not really the controlling factor for this discussion about batteries and engines. Second bullet here is, fuel is a limited resource, okay? We should worry about conserving those resources. So this is a plot in red of the US oil production up to the year of about 2000 here. The blue curve is the curve that was proposed by Hubbard King, a geologist, that involves not just oil, but basically any natural resource that you're going to pull out of the earth, right? And the Hubbard's curve basically shows that you're going to have an increase in production, you're going to hit the peak, right? And then as that resource in the ground is depleted, you're going to have a reduction in the production because of the limited availability of the resource. So circa 2000, obviously for US oil production, we're on the downside of that. And if you look at searches in Google or Reddit from the year 2004 up to 2015, let's say, peak oil is a search term quite frequently, okay? But then at about 2012 here, it almost goes silent, right? And why is that? Well, the answer is that a number of enhanced recovery techniques came into play, and the US oil production, right, has jumped in the last decade or two back to near its peak level, okay? So at least in the United States currently, the availability of resources isn't a controlling factor. And I would argue that we know how to make hydrocarbon, to synthesize hydrocarbon fuels. And so it's an economic problem in the sense that it's far cheaper to drill a hole in the ground and pump oil out than it is to actually synthesize a fuel. But in the short term, I would still argue that we have the ability to produce liquid hydrocarbons for basically onboard energy storage. So that then leads us to greenhouse gas emissions and principally carbon dioxide, okay? So this plot, I think everyone's familiar with, the so-called Keeling curve, where we're looking at measurements of the carbon dioxide concentration on the Mauna Loa Observatory in Hawaii. And over the past 60 years, the carbon dioxide in the atmosphere has increased from a little more than 300 to now more than 400 parts per million, okay? And the argument is, of course, usually made that, CO2 in the atmosphere has always been varying. And so if you go back and look at ice core data and look at the CO2 concentration, so the little bubbles in the ice, you can analyze the amount of CO2 in there. And if we go back now 10,000 years, we see that the concentration for the past 10,000 years up to or so has been about 260 or 270 parts per million until the last 100 or 200 years, okay? You say, oh, that's the when the Ice Age was. Well, we can go back even further in ice core data. So now we're back 800,000 years, and we see that the concentration of CO2 does vary over time, but it's really never exceeded 300 parts per million, okay? And so I would argue then that the effect of greenhouse gases is really the problem that we want to focus on as we compare batteries and IC engines, right? The observed increase in CO2 is entirely explainable by human activity. So you can go through an exercise and prove that that increase in CO2 in the atmosphere is indeed is caused by human activity, right? CO2 has a high greenhouse potential, right? It is able to trap radiation from the Earth as it goes out towards space, and that can and most likely is leading to climate change. Okay, so the first point of CO2 production, that I would say is unequivocal. The second point, you know, people can still argue about how that happens given the long time scale of the climate, but I would argue that it is having an effect. And so I think my point of view is we want to focus on the global aspect of CO2 as the measure by which we're going to compare engines and batteries. All right. So let's move on. Okay. So how do we do this comparison, right? So my dashed black box here is what I'll call a vehicle, okay? And on the vehicle, we have energy storage, and we have some device for energy conversion. And at the end of it, we are going to have a shaft that's spinning, and we're going to extract power from that, okay? So we have torque on a spinning shaft. For a vehicle application, we're going to hook that up to the wheels. For other applications, it might get hooked to a pump or something else. But what we want to do is we want to make the comparison out here, right, on the shaft. So what does it take to make this shaft spin and produce a certain amount of power? Okay, so let's look at first then the case of liquid petroleum fuels, right? So now the storage system that I have is the liquid hydrocarbon fuel. My energy conversion device is going to be an engine. I need to make a few simple assumptions. So the hydrogen to carbon ratio for the fuel, we're going to fix at 2, which is kind of close, a little bit high. And then the lower heating value, so LHV is lower heating value of the fuel, is going to be 42 megajoules per kilogram. That's a typical number for fuels. Okay, the energy conversion process has an efficiency associated with it. I'm going to split this into 2 categories, right? SI for spark ignition engines, so for light duty applications, we'll assume an efficiency of about 0.2, so 20%. Okay, for compression ignition, so like a heavy duty diesel type engine, those engines are more efficient, and their duty cycle is such that they run at higher efficiency. So we'll assume an efficiency of 40% for the diesel engine. Okay. If we do this comparison then on an energy basis, right? So batteries work typically are rated in terms of kilowatt hours. So we're going to do this for 1 kilowatt hour at the shaft. Okay, so that means that this shaft is producing a kilowatt of power for an hour duration. Okay, that's the equivalent of 3.6 megajoules of energy on the shaft. And for the spark ignition case, that's going to consume 0.44 kilograms of fuel and produce 1.38 kilograms of CO2. Likewise, for that same power or some energy, I should say, on the shaft, about half of that fuel consumption and CO2 production for the diesel case. All right, so now we have the case, the electric powertrain, right? So our energy storage device is now a battery, and our energy conversion system is basically taking energy out of the battery and putting it into an electric motor, okay? That onboard conversion efficiency, so eta sub O, we're going to assume at 90%. That's probably realistic, maybe a little bit on the high side. So that's obviously much better than what we saw for the spark ignition engine. But we need to get energy into the battery, right? And so there is a power plant somewhere. And that power plant obviously produces electricity, and then there is an efficiency in line going from the power plant to your charger, right? And the line transmission efficiency is 95%, right? The reference for that number is here. And then we have the electric the electric power plant itself, okay? So this graph here shows the US electrical power generation for 2 years, 2009 and 2019. So orange is 2009 and blue is 2019 in 6 different categories across the bottom here, okay? So let me just quickly go through these categories. So solid, liquid you should just think about it as coal, all right? So that's, most of this is a coal-fired power plants. Gas, these are mainly natural gas-fired power plants. Nuclear, hydroelectric, solar, and then other renewables. And a couple of significant trends have happened in the United States over the last decade, right? So we have reduced the amount of coal-fired power plants by about a factor of 2, right? Most of that has been taken up through natural gas power plants, okay? And the remainder, if you will, kind of that little section at the top there, has been filled with a combination of solar, which in 2009 really wasn't contributing significantly, and other renewables, which you should really consider to be wind, right? So solar and wind have ticked up quite substantially, as has natural gas, all while consuming less coal, okay? And if we sort of pull these numbers together, right? So again, now we're going to just look at 2019. Basically, the first column here represents that chart in the background. So 23% of the electric power generation comes from coal, 38% from gas, and onward, right? The US government knows how much coal went to power plants. It knows how much electricity was generated, and it can tell you then an overall efficiency. So the overall efficiency for coal-fired power plants is 32%. That's an installed capacity number, right? Likewise, same story for natural gas. So the conversion efficiency for natural gas is 44%, nuclear, and then the rest I'll just peg at 100% efficiency, okay? The state of Wisconsin, where I live, has lagged a little bit, let's just say, in terms of the coal. So we still produce about 50% of our electricity from coal, and then you can read the rest of the numbers there. So again, a few simple assumptions are needed, right? So lower heating value for coal at 22 megajoules per kilogram, for natural gas, something like 46. And then at the power plant, we can determine how much, for 1 kilowatt hour at the power plant, what does that require? Well, it's going to require for the US 0.12 kilograms of coal and 0.07 kilograms of natural gas, okay? So a realistic estimate of, how much carbon or CO2 is going to be produced is 0.62 kilograms of CO2 for a kilowatt hour at the power plant, okay? So if we go back and do the comparison on the shaft, then right, those numbers change a little bit. We're up to 0.14 kilograms of coal and 0.73 kilograms of CO2 for an electric vehicle at the shaft, right? And if we combine those numbers in one simple place, so for a kilowatt hour of shaft power, or energy, I should say, this is how much CO2 gets produced. So for the SI engine scenario, 1.38 kilograms. For the electric vehicle scenario, 0.73 kilograms. So a significant reduction in CO2 relative to spark ignition engines. For diesel or compression ignition engines, it's actually pretty close. If we do the comparison for the state of Wisconsin, it's actually, we give back a lot of that that benefit in terms of CO2. Okay, so in a sense, that kind of is the story for CO2, but there's more to this story, of course, than just the impact in terms of CO2. And so we need to sort of look at a few other things. So a very cursory internet search, if you will, look at electric vehicle that are on the market, okay? So variety of different vehicles, try to cover several different makers. The capacity, this is the battery capacity in kilowatt hours, so it ranges from, let's say, 65 up to 100 kilowatt hours. These are all electric systems. The range is the quoted value from the manufacturer from, anywhere from, 330, that would be obviously the heaviest vehicle actually, up to 660 kilometers of range. If we work out kilometers or miles per kilowatt hour, that's this column. So in the best case, we're at about 6.5. And not every manufacturer lists the battery weight, but the ones that do, I give you then the value also in terms of the kilograms for the battery per kilowatt hour. Okay, so some comments on range of electric vehicles. All right, so here's a nice quote, right? So some drivers will get 4 to 5 miles per kilowatt hour, right? Already that's lower than the 6.5 we saw a minute ago. A leadfoot like me driving in the cold, blasting the heater might get only a couple of miles out of that same energy, okay? So that suggests that the end use and the environment of that use is going to have an effect. There's a website, evdatabase.org, which is independent of the manufacturers, that give what they call real range estimation. So very briefly, the right side of this figure here corresponds to mild weather, and mild weather is 23 Celsius and no using an air conditioner. The left side here corresponds to cold weather, okay, which is minus 10 Celsius and the use of a heater in the vehicle. Now, minus 10 Celsius might seem ridiculous in Abu Dhabi, but I will say that in Wisconsin, we go probably, we have weeks in the winter where we don't see a temperature as hot as minus 10 Celsius. So for me, cold weather is a reality. Maybe for you, it's not so much. But if you look at just the bottom number here, which is a combined estimate of range, you go from 445 to 335. So there's a 25% reduction in range corresponding to cold weather. All right. Likewise, if we look at the first 2 rows of either of these tables, right, this is the difference between city mileage and highway mileage, okay? And what we see, the city mileage here is listed in this case here at 390 and the highway at 280. And what's the difference? Well, in the city, the aerodynamic losses are very modest, but at the highway speeds, aerodynamic losses are quite significant. So it takes more energy to push the car down the road fast than it does slow. And then in addition, in the city with a stop-start type driving, you have a significant amount of regeneration. So the net effect is that the city range is considerably higher than the highway range. So there's a roughly 30% reduction going from city to highway. So that means that in the city in mild weather, you might have a range of 570 kilometers, which is of course what the manufacturer puts on their advertising. But in reality, for highway driving in cold weather, you're at roughly half of that. Okay, so there's a significant difference in range than what is expected. Okay, so we'll keep that sort of in our back pocket. And we need to talk a little bit about charging. So different vehicles have different recharge rates. So this blue column here, right, the first two columns are what we saw before. The blue column is the published recharging rate, and it ranges from 50 kilowatts up to, I guess, 270 here for the Audi. So what are sort of conventional chargers? So a level 1 charger is basically just plugging it into the wall in your house, okay? So that would be 2.4 kilowatts. If I wanted to have a level 2 charger at my house, I would have to have a special high voltage feed installed, and that would get us up to 19 kilowatts. Fast chargers, or typical fast chargers, are 50 kilowatts. The Tesla supercharger, which they're building a network of these on highways, is at 120 kilowatts. The two gray versions at the bottom here are somewhat experimental demonstrations where 350 and 450 kilowatt chargers have been built and demonstrated. Okay, I just put an asterisk here, right? The Kia value 179, that came about because they didn't actually list the actual recharge rate. Later, I actually found it at 250 kilowatts, but the 179 comes from their statement like this, which is representative of all of these vehicles. And it says, you can go from 10 to 80% charge in 18 minutes, okay? So that's different than saying I'm gonna put the full 77 kilowatt hours in 18 minutes, or put the full 77 kilowatt hours in at 179 kilowatts, which would mean I could do that in 20 minutes or so, okay? So we need to understand better the issue of battery charging. I don't know anything about that, like I showed you before, but I found this review paper, a relatively recent review paper about fast charging lithium-ion batteries. So to start with, we need to understand a little bit about how lithium-ion batteries work. So we're going to start with looking at charging, right? So the battery structure is like you see here on the left. This sort of black bar represents the negative terminal, or the anode of the battery. On the right, this black bar is the cathode. The cathode material is some sort of lithium oxide. The anode material is graphite. And for charging purposes, what happens is the following. There's a lithium atom in the cathode. We're going to strip an electron off of that lithium atom, okay? And that electron then obviously goes into the charging circuit, and that leaves a lithium ion at the surface, that needs to get migrated to the surface of the cathode. It then transports across the electrolyte to the anode side, right? So now I have the lithium ion at the anode. It combines with the electron, produces a lithium atom. that lithium atom now needs to basically get out of the way, if you will, right? So it needs to diffuse into the anode, into a storage site for storage for later use, right? And that later use is when you discharge, and this process reverses. And that is that lithium atom that we put in the anode, we're going to strip the electron off of that, make a lithium ion. It's going to transport over to the cathode, and that electron then gets used in the circuit. Okay, so that's the fundamentals of how a lithium ion battery works, right? So some comments then, or a discussion of fast charging, right? So the first is that the charging rate is controlled both by the charger and a battery management system, all right? So there is a very sophisticated set of software that controls how the battery works, and that's critical. So what one takeaway from this is that even though the charger, the Tesla supercharger might be at 120 kilowatts, the battery management system is not going to allow 120 kilowatts into the battery unless it thinks it can handle that. Okay, so it will throttle the rate of charging to be appropriate for the battery at its current state. Okay, typically the charging rates are limited to 1 to 1.5 C. The C rate is a battery term that defines how fast it's either charging or discharging. So 1 C means, if we're talking about charging, that you can fully charge the battery in 1 hour, right? So 2 C then means you can charge it faster, which would be a half hour, okay? The Porsche system that we looked at a minute ago is a 3 C system. All right, the second thing is that this is a chemical process, right? So that physical transport, it's a chemical and transport process. I should maybe say it's a little better. And those of us that grew up in the combustion world know sort of one thing about chemical processes, and that is they're nonlinear and they're very highly sensitive to temperature, okay? And the other thing we know about chemical systems is that usually there is a rate limiting step in the process. And in this case, for lithium-ion batteries, the rate limiting process is the rate of lithium diffusion into the anode. Okay, so let me go back up and explain. Right, so the lithium ion comes over, lands on the surface of the anode, right? It combines with the electron to make a lithium atom, and then it has to diffuse into the anode for storage purposes. If it doesn't diffuse in fast enough, meaning before the next lithium ion comes, you can actually plate the surface of the anode with lithium, okay? And that's what I'm saying here, is that, the rate limiting process is really this lithium diffusion in the anode. The failure mechanism, if you will, is the lithium metal plating the anode surface, all right? So low temperatures inhibit this diffusion rate. So actually for fast charging of batteries, you have to preheat the battery, okay? So there are heaters in the battery to bring it up to temperature to allow to basically increase that diffusion rate to allow faster charging. The second bullet here is that limited site availability also inhibits the diffusion rate of lithium. So if that anode is full or almost full, it's hard to find an empty spot for the lithium atom to get stored. And so as the state of charge increases, meaning you fill your battery up, site availability decreases. And that's why there are statements of 10 to 80% or something like that for fast charging, right? So you can fast charge up to, let's say, 70% of the battery capacity. And then from that point, if you keep charging too fast, you're just going to plate lithium on the surface, and that causes the problem that's in the third bullet here. And that is that if you've got lithium plated on the surface, that lithium isn't free to carry charge across across the battery. And so you lose capacity because of that. And then obviously high current is going to cause problems as well. And I think we're all familiar with sort of self-heating and thermal runaway issues. Batteries obviously aren't cheap or free for that matter. So here's a recent article saying that actually have crossed below $100 per kilowatt hour. If you look at this trend over time, you see that out here about 100 kilowatt hours is right based on the trend line that you see. Okay, so with that as background, now let's do some comparisons for a light duty vehicle, right? We're going to do the comparison for 77 kilowatt hour battery, right? The 6.4 kilometers per kilowatt hour and 6.5 kilogram per kilowatt hour come from previous data that I showed you. The gasoline, we'll assume a 53 liter tank and a density of gasoline of 0.75 kilogram per liter. And then we're going to do all of these comparisons again at the shaft itself. So if we look at the onboard storage for those two scenarios, the green is the electric, the red is the gasoline, and we see in terms of shaft energy, it's actually quite comparable, right? So we get, 69 versus 90 kilowatt hours. If we look at range, under all the assumptions above, right, the gasoline gets you 643 kilometers, mild weather, city driving puts you at 493. So again, not too far off. On the other hand, if we're on the highway and it's cold, now the range is going to drop by about a factor of 2. Weight, well, here's where we start running into some issues. So the battery is going to weigh 500 kilograms. The fuel load is going to be 40 kilograms. So there's a significant penalty in weight, to say the least. On to sort of the recharging, right? The US EPA limits the flow of gasoline at a gas station, right? And that is limited to 10 gallons per minute. That works out to 21.5 megawatts of power. And if we look at the energy recharge rate, again, in terms of shaft potential, we're doing this for the Tesla supercharger, right? For gasoline, we're at 4,300 kilowatts. For electric, we're at 108, okay? So 40-fold difference in recharge rate. A few other comments, right? The full range for highway travel is about 25% lower than the manufacturer quoted value, which is the city value. So instead of roughly 500 kilometers of range, we'd really have about 345. And if it's cold, we're down to about 260, okay? The recharge is limited to, roughly speaking, about half of the capacity of the battery. And that usually, most manufacturers quote that at about 15 minutes, so a quarter of an hour. So that's a 2C rate, okay? So really, what does that mean? It means if I want to drive a long distance, okay, I'm only can really do it for about 50% of the battery capacity, because otherwise it's going to take significantly longer to recharge the battery. And that means that I go from now 345 down to about 170 kilometers of range, right? So the quoted value was 500. Effectively, we really can only go about 170 kilometers if we want to have a fast recharge of the battery. Okay, just showing you these numbers again, right? In terms of CO2, there's still a net win in the electric world. Some comments about the light duty application, right? So at highway cruise speeds, SI engines are actually significantly more efficient, probably 35 or 40% efficient. So that CO2 penalty is much less. The CO2 for the battery vehicle is coming via, basically how we produce electricity in the United States. That will continue to decarbonize. That's a good thing. The issue is the lower level of that is sort of a base load. So at night when the sun isn't shining and no wind is blowing, I still want to run the refrigerator in my kitchen. And so that base load currently is coming from nuclear and fossil fuels, and nuclear isn't growing in this country. So there is basically, the floor for fossil fuel production of electricity is not zero, I would argue. Urban driving, it should be done on electric power, right? There's a CO2 benefit, and in addition, it's going to improve the local air quality. The flip side is that batteries are not, in my opinion, a good power source for long distance travel, because rapid recharging only is going to give you about 50 or 70% of the battery capacity, still takes 15 minutes, and the range estimates are what we discussed a minute ago. So we have significantly shorter range. If I have to stop every 150 kilometers for 15 minutes, that's not a workable solution. Okay, heavy duty vehicles, right? All my other comments, all the comments I've made so far still apply. A typical Class 8 truck. So a Class 8 truck is a over the road, a semi-trailer type truck. They typically have about a 200-gallon capacity, and that gives you a shaft energy of about 2,900 kilowatt hours, right? Variety of different manufacturers have said they're going to build electric trucks, capacity range up to 1,000 kilowatt hours. That really isn't a quoted number. That comes from Tesla's estimate of 2 kilowatt hour per mile, and their stated range of 800 kilometers. Couple of things, right? So in the US, the gross vehicle weight, right? So that's the cab and all of the freight is limited to 80,000 pounds or 36,000 kilograms. At 100 kilowatt hours, we're looking at 6,500 kilograms of just the battery weight. The split is roughly half and half between the weight of the trailer and the weight of the cab, meaning the part that's driving the truck. Okay, so a significant reduction in capacity because of the weight of the battery. The other thing that I'll point out is, again, the US government knows how much diesel fuel goes into these trucks and how many miles are covered. So that gives about 6 miles per gallon of diesel for over-the-road trucks. And that works out to 6.25 kilowatt hour per mile. So obviously a difference versus what's being quoted from the electric manufacturers. Okay, and again, for long haul applications, the CO2 potential or benefit isn't as significant as one might like. So my opinion is long haul applications are not viable at present. And based on what we just looked at on the previous slide, the electric heavy duty vehicles are really targeted for last mile delivery, right? So, urban transport of goods, and that's totally reasonable. You have significant regeneration. There's significant benefit in terms of local air quality and efficiency, okay? For long haul applications, the CO2 considerations really aren't there. Just very briefly, off-road applications, if you don't have a charging infrastructure, which maybe in your, if you're thinking about forestry or something like that, then none of the electric makes any sense, right? So if you have to burn fuel to make the electricity on site, you should just burn it right in the vehicle. A couple of final observations about batteries, okay, and these are again on a shaft energy basis, and we're doing this comparison with gasoline. You store a comparable amount of energy for the light duty. You have a higher upfront cost. So HEV, so hybrid electric vehicle, plug-in hybrid vehicle, an electric vehicle, you know, so from $200 to $7,500 are just the battery, okay? They're cheaper to operate. So this is the rate of, we're charged for electricity in Madison, Wisconsin. That works out to about 16 cents per kilowatt hour at the shaft. For gasoline, this is a US average number, and that's 38 cents per kilowatt hour. So it's somewhat cheaper to operate. They obviously are going to weigh substantially more, takes substantially longer to refill. They have a lower carbon footprint, but the benefit is they confine hazardous air pollutants to the point source of the power plant. All right, so are batteries able to replace IC engines? So my argument is yes, but there are always buts that go with it. They only make sense for urban and short distance travel, in my opinion. The rapid recharging problem, it's limited by physics. So Elon Musk can't wave his magic wand and say that, you know, he's going to automatically refill your battery. Physics is involved, and that is going to be really the problem, right? And I don't see that problem as moving by 2 orders of magnitude like it needs to. The ultimate answer for CO2 is really going to be this competition, right? So if we are going to have zero net carbon electricity production, the way that has to be enabled is through large-scale energy storage, okay? So that way we can have complete renewable fuel for electric power generation, and then the battery option actually becomes very low CO2. And the competition is then between that solution and the solution of having an economically feasible low net carbon fuel, right? So if I can have basically zero net carbon fuel and burn it in an engine, for example, for long haul truck applications, that's that would be a good option, quite frankly. So one caveat, right, that really to do this correctly, you need to do a very rigorous analysis for actual driving data and a complete well-to-wheels analysis. And, you know, batteries, you know, have kind of been given a free pass, but, you know, lithium isn't free. It comes by, you know, scraping the earth and pulling the lithium out of that. When you're done with the battery, it doesn't just evaporate, right? So, you know, there are costs and environmental costs associated with both the production of lithium. It's going to be subject to that Hubbard curve that I showed you earlier. And then also the recycling of the battery when it's done. So, so just sort of in a closing, so what does Jaal drive? Well, what I drive is this car right here, which if you didn't notice has 2 holes in it, okay? Right, it has a charging port in the front and it has a gas filling port in the back. So I drive, it's a Kia Niro, it's a plug-in hybrid vehicle. It has roughly 9 kilowatt hour battery that gives you about 40 kilometer range. Madison is a, you know, small to medium sized city, so I can do all my driving around town fully electric. The engine in the vehicle actually has a peak thermal efficiency of 40%. You can read about it in this SAE paper here. And so on the highway, I can disable the electric and make it a full hybrid vehicle and, you know, basically get the benefit of that. So just quickly in closing, right, all of this is, if you will, my crystal ball. If you look through this crystal ball, you see that it's very cloudy. I think everybody's crystal ball is that way. So, so I might revise these comments in 5 or 10 years from now. And with that, I thank you for your attention, and I'm happy to answer any questions that anyone might have.
Thank you very much, Jaal. It comes as no surprise that this exciting talk has generated a huge number of questions in our chat. I will try to group some of them for you, and then if you go through and find something interesting, you are welcome to address it yourself. So a couple of colleagues are asking, should we also consider CO2 emissions related to liquid fuel production, like it's shown here for the process of electricity production? And similarly, battery production emissions should be added into the considerations. Would you like to address that?
Yeah, you bet. So are you still seeing my screen?
Yes.
Okay, so hopefully you're seeing slide 30 here, right? And so as I said here, you know, rigorous analysis is going to require a well-to-wheels analysis, and that's both sides of the coin, and that is for the, you know, the gasoline production, you know, as well as the, you know, producing the battery and all of that. And so absolutely, that's going to be required. Those analyses, you know, I'll, you know, freely admit that, you know, I simplified this problem quite substantially. And the reason I did that is, you know, I wanted everyone to understand all of the assumptions that went into it. And, you know, these are just simple multiplications at the end. And the, you know, as you increase the complexity of those analyses, you end up introducing lots and lots of assumptions. And so, and in many cases, those assumptions become, you know, controlling. So, you know, yes, I fully agree that you need to do that. But I do worry that, you know, just for the simple argument, the scaling type argument that I think I put forward here, it is going to maybe add more uncertainty than anything else. And I'll give just sort of one example. For years, there were arguments about ethanol production and whether it was, you know, actually took more energy to produce ethanol than the energy in the ethanol itself for, you know, for fueling vehicles. And, you know, that argument is pretty much settled, that you actually now, you know, the scales have been tipped and it is beneficial to produce ethanol. But it all hinges on what you do with the waste streams from the production. And so these are, you know, sort of complicated arguments, and it's, you know, tied up in those assumptions and that accounting. So that would be my comment.
Very good. And this brings actually to a second line of questions that we have here, and asks whether we have reached the IC's peak in terms of efficiency, and especially in relation to the use of alternative fuels like the ethanol that you talked about, and or perhaps hydrogen.
Yeah, so so no, we're not at a peak. I don't believe. I mean, I can say that categorically, right? We will continue to see incremental increases in engine combustion efficiency. Okay, and in some cases, ethanol being one, you can actually make the argument that I can build a much more efficient engine if I know that I have ethanol available as my fuel. Okay, so I think those two things can pair together to improve efficiency, but there is going to be a limit to it, right? It's not an endless path to 100% efficiency. That's for sure. I guess I'll just leave it at that. I mean, you know, we continue to see improvements. Well, I guess let me add one other thing. So, you know, engines are actually very efficient, right? So over-the-road diesel engine, those, you know, have peak efficiencies pushing 50%. Okay, if you remember the chart I showed you of conversion efficiencies at power plants, you know, for coal-fired power plants, it was like 32%, and for natural gas, it was like 42%, right? Modern natural gas power plants can push up into the 60, 65% through lots of different, you know, recuperation stages and things like that. So in the mobile application, to get 50% efficiency is incredible, right? Now, where they fail is at light load, right? The efficiencies at light loads are quite poor. And so the marriage of an electric powertrain with the gasoline engine makes sense, right? Because at light load, you have the efficiency of basically the grid. If you have a large enough battery to handle all of the sort of urban transport, and then, you know, at, you know, highway speeds, you can rely on the engine, you know, get the full conversion efficiency benefit for the engine. So I see that as a more likely scenario for the next 20, 30 years, is that marriage. I don't think that the sort of jumping over the top to get to the full electric is necessarily the correct answer.
Thank you. Another line of questions relates to alternative electrochemical sources of energy storage, like lithium sulfur batteries, and notably fuel cells. Would you like to comment briefly as to their prospects?
So, so I don't keep up on that in any level of detail. So I really, you know, can't comment in any. I can't comment fully on that. I would just say, right? I mean, absolutely, there are different formulations out there. There isn't, I would say, a large push to move that direction currently for mobile applications. For stationary applications, I think that's a different story, but for mobile applications, haven't seen that yet. In terms of fuel cells, you know, again, it's probably a great, I'd say a great technology, but there's still, you know, energy storage issues there in terms of purity and things like that that have kept fuel cells from basically taking over.
All right. We are a little bit past our time, and we will conclude this with a very practical question that probably comes from one of our students or young scholars who are planning for their career. And it reads, do you believe that batteries replacing IC engines would have a negative impact on the number of jobs available for mechanical engineers?
Oh no, on the contrary. You know, so the problem of energy conversion, I argue, is still a huge part of mechanical engineering, and the thermal aspects of batteries is critical. And so I see no limit in terms of, you know, what mechanical engineers are going to do in the future. And let me sort of go one step further, right? You know, if you went back 100 years and said, we're going to take, you know, a chemical, we're going to combine it with air through some sort of chemical reaction and try to make the shaft spin, you would have said, oh, I need a chemist to do that. You know, the only thing a mechanical engineer needs to do is sort of build a mechanism, right? And I think we're in the same spot in that, you know, let me just finish my bias on that. And my bias is it's been mechanical engineers that have done the combustion work for the intervening 100 years. And so I see this energy conversion problem, you know, as never going away. Whenever you are talking about high powers, right? So what happens? Well, we don't want to just convert energy. We want to do it fast, right? So I don't want to just drive, you know, I want to drive fast. I want to get someplace. And so it's an issue of power. And so anytime you're dealing with power, there are going to be thermal constraints that go along with it. And that's, you know, something that mechanical engineers have been dealing with for a long time and will continue to deal with into the future. So
So
a bright future for mechanical engineers.
fantastic. And on this bright note, I would like to thank you once more for offering your time today. It was a distinct honor to have your insights on what has emerged as a very relevant issue in contemporary mobility engineering. Likewise, I would like to thank everybody for their attendance, and we will be in touch with further seminar announcements from both the UAE section of the ASME, as well as more technically focused rich seminars on carbon neutrality and hydrogen economy. Thank you very much, Jaal, once again, and thank you everybody for your attendance.